Hi students, good morning everyone. We have 3 more minutes to start the class. So just waiting for the persons who are going to add the class. Okay. Okay students, good morning everyone. So today we are going to know about the chapter Unit 2, Time Response Analysis. So before going to know about the time response analysis, we are going to know about what is meant by response. So response is nothing but output. So when we give response, response is nothing but respond of the system, respond of the system. So respond of the system. So when we give a input to the system, then the system gives some response. That is not see, we can in our general words we call, hey, he doesn't give any response to the what we are asking, like that. Okay. So here the response, we are going to analyze the response with respect to time. The time response analysis means we are going to analyze the response of the system with respect to time. So this is nothing but we are going to analyze the response of the system with respect to time. See, generally in our previous chapter we are discussing about what, discussing about the so let us take the transfer function of a system. So let us take the function. We are what is by transfer function. So transfer. So C of s by R of s is equals to G of s by 1 plus G of s into H of s. See here all the functions with respect to S domain. So all the functions are in S domain. So S domain. Here this not just response. Okay, that's why we are going to take that response itself. Okay, so C of s is equals to R of s into G of s by 1 plus G of s into H of s. You clearly understand how it comes? From this closed loop transformation we can derive this expression. Okay, so here all the functions are in S domain. So we are going to, this is the Laplace transform. So C of s is Laplace system. So C is the transform to the system, and R of s is the Laplace transform of the input. So we are going to convert this S domain to time domain, frequency to time domain. That's why we are going to inverse Laplace the whole function. Inverse Laplace the C of s with respect to C of t. So we convert the s in terms of t. So for that purpose we have C of s is equals to R of s into G of s by 1 plus G of s into H of s. Okay. Now we are going to inverse Laplace this term. So inverse Laplace of C of s is equals to inverse Laplace of R of s into g of s by 1 plus g of s into h of s. Okay. Now what happens? The c of s becomes c of t is equals to inverse Laplace of r of s into m. C of t into m into r of s, where m is equals to g of s by 1 plus g of s into h of s. Okay. So here this is the process how we convert the output response with respect to s domain to t domain. T domain means time domain. So see here, this is the time response analysis of the function, this function. So this is the time analysis of the function g of s by r. See here, total the transfer function, it is with respect to s domain, frequency domain. We convert this response in s domain, frequency domain to time domain by taking inverse Laplace transform to the s domain. By taking the inverse Laplace to the s domain, we convert this s domain into time domain. Okay, students. Okay guys, you tell to your friends and everyone in your class, both ECE, A and B, and all, to come and join the class. Okay. So this is the time response analysis introduction. So we are going to convert the s domain function into t domain function, time domain function with respect to t. We are going to by applying different signals, test signals. Next hour we are going to discuss about the test signals. Okay. So by applying that test signals as input, we got an output, and we are going to analyze the response with respect to time. Okay. Now we are going to know about the test signals. Okay. So our next topic is test signals. You are all know about the signal. So signal is a thing, we are going to give it as an input to a system, and by that input we got output. Okay. So lab so there are 5 types of signals are there. First one is step signal, second one is ramp signal, third one is parabolic signal, and fifth one is impulse signal, and last one is sinusoidal signal. Okay. So now we are going to draw a closed loop transfer function, closed loop block diagram. Okay, see here, R of s, G of s, C of s, H of s. So by taking this Laplace transform, inverse Laplace, we convert it S domain to T domain. Why? Because we are using here so see here what happens. So this is the R of t. So R of t here in the, it is the input of the system, and C of t is the output of the system, and H of s is the feedback signal. We all know that. So in this place of R of t, we can give these signals as input signals. Okay, we can give the step signal input as an input here, and ramp signal, parabolic signal, impulse signal, sinusoid. So all the signals signal this some output type. Okay, we are going to get some output signal, that is nothing but response with respect to time. With respect to time. Okay, with respect to time. Now we are going to the, so why we can take these signals as a test signals, means these are easily generated in the laboratories. These are easily generated in the laboratories. Okay, this is generated in the laboratories. So this has a good mathematical equations. These have good mathematical equations due to some characteristics. These are taken as a so first we are going to know about the step signal. Okay, firstly we are going to know about the step signal. See here, this is the waveform for the step signal. Zero. R of t. T. Changes from 0 to A. From 0 to A are 0 to A. When t is equal to 0, it changes from 0 to A and remains constant. At A for t is greater than 0. So this is the expression. See here, 0 to A. So A is the magnitude of the response. So for any time, at any time it remains constant, except from 0 it changes from 0 to A. At the t, so we can write a expression for this. So the mathematical expression is R of t is equals to A into U of t, where U of t is equals to 1, that is t is greater than or equal to 0. Why? Because this is belongs to step units. A for unit step a is equals to 1. U of t is equals to 0 or t is less than 0. So this is the mathematical equation for step and unit step. Okay, this is the waveform and this is the mathematical expression. Please note everyone. Okay, now we are going to know about the ramp signal. I hope you all noted this one. Okay, now we are going for the ramp signal. So coming to the ramp signal, the signal whose value increases linearly with time from an initial value 0 at t is equals to 0. Okay, let us see the waveform. Okay. Zero, R of t, A, 2A, 1, 2, t. So this is the increases linearly with respect to time from an initial this point t is equals to 0. So for 1 it is increasing up to a. So and for the 2a. You understand what I am saying? So it is linearly increases with respect to time. Linearly increases with respect to time. The ramp signal resembles a constant velocity input to the system. So this type of signal represents the constant velocity. So it can linear means with a periodic intervals of time. Okay, constant velocity input to the system. Okay, let us see the mathematical equations. R of t is equals to at. R of t is equals to at when t is greater than or equal to 0. So R of t is equals to 0 when t is less than 0. So in some special case, ramp signal is unit ramp signal in which value of a is unity. So for unit ramp, the a is 1. So R of t is equals to a into t. A becomes 1t. Then t is greater than or equal to 0. This one is for the unit ramp. Unit ramp means its magnitude is 1. Okay, it should be 1. That's it. Okay. And this is the mathematical relation for the ramp signal. Note down, everyone, note down. And next one is parabolic signal. So this signal waveform represents the constant velocity. It's a very important point, constant velocity. And next, coming to the parabolic, it is a constant acceleration. Okay. This is a parabolic signal, the instantaneous important one. So we're going to know about zero, 0.5 amps, 2 amp, 4.5 amp, 1, 2, 3. Varies as square of the time. So see here, this is the time and is a response and instant value. Is instantaneous value. So the instantaneous values varies a square of the time. Okay, square of the time for an initial value of 0 at t is equals to 0. So from this we can write an expression r of t is equals to a t square by 2, where t is greater than or equal to 2 that is equals to 0. R of t, when r of t, so r of t is equals to, when r of t is equals to 0 means t is less than 0. See here, from here only the r of t value is gradually increased. So see, r of t is equals to a into t square by 2. See here, when t is 1, r of t value is 1 by 2, a is 0.5, 1 by 2 0.5. That's why we came. Okay, let it be 2 is when t is equal to, for example, substitute t is equals to 1. What happens? R of t is equals to, what is the value of a? A into 1 square by 2. 2 ones are 2, 0.5. That's it. Okay. Okay guys, we have to see the mathematical equations for step, ramp, parabolic, and we are going to see about the equation for impulse signal. Okay, I think everyone note down this one. Everyone note down this thing. Impulse signal. So now we are going to draw the waveform of the impulse signal. So this is the R of t and t, the impulse signal A. So a signal which is available for very short duration is called impulse signal. Okay, the very important point is the signal which is available for very short duration is known as impulse signal. That's why we call it as here 1 by A, the value is, okay. So ideal impulse signal is unit impulse signal which is defined as signal where having zero values at all times except at t is equals to 0. So it has the value is only for, see, it's a very short time at t is equals to magnet. That's why we got the signal delta of t is equals to 0 for t is not equal to 0. When t is not equal to 0, at the signal t is not equal to 0 means these are all not equal to 0. Only one point t is equals to 0, remaining all of t is not equal to 0. For all these time divisions, delta of t is equals to 0. That's why we call the impulse signal is a very short signal. The signal is available for a very short time. Okay. And Laplace transform t tends to 0, integral of minus t1 to plus t1 delta of t dt is equals to 1. This is a very important formula for the impulse signal. Now we are going to see the now we are going to see the standard test signals table. Name of this signal, time domain equation of signal, time domain equation of signal, Laplace transform of the signal, Laplace transform of the signal R of S. Here it is the R of t. So for step signal, step time domain is A, and the Laplace transform for A is A of s. Unit step and its magnitude is 1 and 1 by s. Next, this one is for step and ramp, unit ramp, parabola, unit parabola, final one is impulse for the impulse signal. Okay, so for the signals we are going to show the time domain equation of signal R of t, and ramp signal is at, unit ramp t. So here the Laplace is a by s square, 1 by s square is the R of s time. R of s in s domain, the values are 1 by s square, like that. Parabola is a t square by 2. These are all the mathematical equations what we have seen in the earlier mathematical equations. Okay, so a by s cube is the response. T square by 2, 1 by s cube. And for the impulse one is delta of t, that is equals to 1. For what we are discussing here is for Laplace transform of delta is 1. That comes here. Okay, so these are the values of the standard test signals. So by knowing all these things, we are going to, by using these input signals, response, time domain responses, and Laplace transform of the signal, we are going to, these are all the inputs. Okay, these are all the inputs. See here, Laplace transform of R of s, we are going to convert this R of s into time domain. Okay, C of t. So we are going to analyze the signals with respect to time. So these are all the with respect to signals, input signals with respect to s, and R of t is the input. Okay, input with respect to time. We are going to find the analysis with response analysis with respect to time. By using these signals, we can apply step signals for systems. We are going to find the time response analysis. Okay students, I hope you understand the class today. If you have any doubts, comment me and I can clarify it for you. Okay, thanks for watching.